Okay, so we're going to have a quick look at the first test for e-security. So the main areas that we're going to cover are basic ciphers, some fundamental things like GCD, large numbers, and then also onto public key, private key, and key exchange, hashing and signing, and digital certificates and authentication. Really, these three units all really fit together nicely, and you really need to understand all three of them together to really understand the infrastructure of cryptography. Okay, so make sure you've done the labs, the basic labs there, so that you have some practical skills in actually analysing and implementing your cryptography. So the main study guide is here, so if you just click on this button, so there are a few things that you might want to know. But if you just scroll down, then you'll actually find there are a number of questions that are posed here. Okay, so certainly you need to know what public key does to be able to show both privacy and also identity verification. So have a look at the lecture on this, and hopefully you should be able to identify the key aspects, to use a bad pun, sorry, of the elements of that. Okay, so try and understand what public key really gives us, and that the way that we use the private key to be able to prove identity, and then Alice's public key to be able to encrypt data. Okay, so also try and look at streams and block ciphers, and why we use salt within that. So if you flick forward to Unit 2, I think it's in slide 15. And in slide 15, we outline the basic methods are in terms of creating our cipher blocks. And let's scroll to that one. And we want this one here. Okay, and it's all to do with electronic codebook, which is really quite weak. With electronic codebook, it's possible to be able to create the same cipher block for the same content. Okay, so we've got some examples online if you want to have a look. So often what we do, well, mostly what we do is that we add salt, and the salt is in the form of an initialization vector. So one method that we can use is cipher block chaining, where we take our I initialization vector and exclusive or the first block, and then we take the encryption key, then we feed forward. Obviously the problem with this method is that we've got to actually decrypt all the information and all the blocks to be able to decrypt the actual message. With our stream cipher, then we can actually encrypt one bit at a time, so we can decode in real time, whereas in our blocks, we've got to wait for the blocks to be delivered. Okay, so obviously salt is very important too when it comes to the hashing process. With salt, we change the hashed value dependent upon the salt. So we'll take the password, we'll add some salt to it, and then that will produce our hashed value. So have a look at Openssl and how Openssl is used to prove the hashed value, where we take the password and the salt value and then find what the hash actually is. Okay, so have a look also at the different types of hashes that we actually produce. So with computing power, we increase, let's say we double every year. If we double every year, then we half the amount of time it takes us to encrypt, and we keep half. Basically, we lose a bit if we double the computing power. So the advantage of stream over block, obviously it's faster, it's simpler, and we can obviously decrypt in real time. With this one, if we encrypt with his private key and sends to Alice every time he produces ciphertext changes and he's worried, have a think about what's actually changing the cipher. This one too is also looking at ECB. So again, try and understand what ECB actually does, especially have a look at the penguin and see what happens with the penguin. Even though we use very strong encryption, we can actually still see the penguin. And then we come to key entropy. With key entropy, often we don't use the full key space. So for 128 bits, it's 2 to the power of 128. But obviously, if we use a password, then sometimes the passwords are fairly limited. So we need to understand the equivalent size of our key that we would have when we use a passphrase to generate the encryption key. Okay, so be ready to be able to calculate basic entropy. And a key pair, if Bob has a key pair, do you think he really sends that to Alice? Is that a good idea? Okay, so also have a think about digital certificates and how Alice proves Bob's identity and what keys are used for that. And then when it comes to hashed passwords in the cloud, think about the tools that are actually used in that. So I've put a little article here which gives one viewpoint on cloud cracking, but now we can in the cloud we can make use of processing elements with multiple cores on them, typically using the CUDA architecture there, and that significantly reduces the amount of time because we can split the task into parallel tasks. So for example, if we have 4,000 cores in an NVIDIA GPU, it will often take 1 over 4,000 times shorter, or 4,000 times shorter than it would without them. Okay, so the password file, have a look at the software hashes lab, and there's an example in there that actually shows you most of the hashing methods. Okay, so there's the format that we have. Okay, we sometimes have a number of rounds that we go through, and at the very end we've got this part here. This part here is quite interesting because it actually shows us how we can actually compute all the hashes. If you have some time, have a look at it and see the types of hashes that are actually produced. You should only need hashlib and passlib to be able to get it to run, and from there you'll be able to see the different types of hash values and the salts that's actually used them. Okay, so if Bob is looking for a new hashing method for his strong passwords, should he choose one that's really fast? So we get methods such as XX hash and so on. Are those really good methods for creating a hash? And I've got a little article there that you can read. And what are the tools that we use for cracking our hashes? Have a look at lab 2 and you should be able to see it. And then try and understand the concept of GCDs, because it's very important in terms of selecting numbers for our encryption keys for E and D in public key encryption. And then there's a little paper there that you can actually have a look at that you might want to investigate. It's got those questions that we've just looked at, and it's got a few other ones related to Hellman and key entropy and so on. Okay, so if you have any questions, just ask. Thank you.